Hello, good evening, everyone. Am I audible?
Yes, good evening, sir.
Good evening, sir. Yes, sir. Audible, sir.
Okay, thank you. Thanks for confirming. So, today we are going to see week 2 of MLT course. So, you have already done week 1, right? Last week. So, how many of you have gone through the content of week 3?
Sir, week 3 today, yesterday.
Sorry, week 2, week 2.
Yes, sir. Week 2, little bit gone through, sir.
Okay. So, how did you find it? It is tough or easy?
Still, we have to see, sir.
Sir, I felt a little tough,
Tough.
sir.
Okay.
The concept,
What about?
I think once more, if we see the lectures, maybe we'll understand.
Yeah.
But I was able to do the sums, but
Hmm.
somehow a little dry, the
Okay.
kernel part.
And what about week 1? I hope everyone has done week 1 already. If you haven't done week 1, week 2 won't be easy for you.
Week
So I
okay.
recommend first go through the week 1 and then come to these sessions. Otherwise, you can go watch week 1 and then come to the recording part later. Because if you haven't done week 1, week 2 will be gone. So
Sir, why are we not having solve with us sessions like we used to have in the last term?
this time also we have the solve with instructor. We have on Sunday 10 to 12.
No, we never had that. In fact,
So
yesterday,
last week we didn't have, no, sir.
Oh, I'm not sure about the last week, but this week we'll have one session on week 2, which is on Sunday 10 to 12.
Sir, one more thing I had requested and I had put a message also in discourse that BDM project session and this MLT session is clashing. And we asked Aditya, Dr. Aditya, who's an instructor, who's a professor for BDM project. He said he's been
Hmm?
having this his session for the last 7 years at the same time. So he asked us to send a message to you. So we put a message in the discourse to you and copy to Bharati ma'am. I put, but
Hmm?
there's no reply. I didn't get any reply. So are we going to shift the last week also? I requested because they both are clashing, and it's very important for us to attend that session also.
Okay, so I was not sure. I was not aware of this. I'll inform my team and even
Sir,
the
your
operational
good
team.
name, sir?
Nitin.
Oh, okay, okay. I last week I think we had Jimmy, sir.
Yeah, last week Jimmy took the session.
Okay, 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 okay. I had put a message, tagging him only in the discourse. So,
Yeah, I'll let my team know this and we'll try to sit this session.
thank you, sir.
Mm,
Thank you so much.
Sir,
Can't be.
there's one Thursday session of Thursday TA session also clashing with DBMS session. So,
TA sessions, I'm not sure whether we can shift or not.
sir, it's very important for us because we can clear our
Okay,
doubts.
I'll convey all those things. Even I'm not sure about the TA sessions, but this session we can shift to another some other time. Uh,
One more thing, sir. Last week, Thursday, TA session was not there. TA was not there, sir.
last week or this week?
No,
This week,
This
yesterday.
week,
yesterday,
this week.
yesterday, sir.
This week,
Yesterday.
and even before that also, one day. Totally, we had after the course started 2 or 3 sessions, isn't it? So two
yeah,
sessions.
yeah, 3 sessions.
Okay,
Three
okay. And
sessions.
did you get any announcement regarding that?
No, sir. We waited nearly for half an hour yesterday, but nobody joined. No, none of the TAs joined. So we had to
Same
exit.
thing happened last week also.
Okay.
So there was no message, no information. We all just
Okay.
sitting for
So
nothing.
let's do one thing first. Let's start week 2 because it's going to be live stream. So we can discuss this thing in the after the session after this
Okay, sir.
once we go through the content of week 2.
Sir,
So
one more query. Did we had any recordings for the week 1? Because I was trying to find out. I did not get anything.
it must be there because every session is being recorded.
No,
It
it
is
is
there, sir, but it is not updated in the calendar. It is, you can find it in the MLT channel, YouTube channel.
Okay.
MLT YouTube
We'll
channel.
update on
Okay.
the because I'm a part time for this MLT course. full-time
Okay.
instructor from some other courses. That's why I'm not very sure about this course. What?
Can somebody ping me the link of MLT YouTube channel? Because I was trying to look for it and I could find only September 23 MLT course link.
Okay, all those things we can discuss later. Let's get started with week 2 first.
Sure, yeah.
Yeah, okay, because it's already being live stream. So let me share my screen. I hope my screen is visible to everyone.
Yes, sir.
Yes, sir.
Okay, so okay, so let's start. In week 1, you have seen how to find the principal components, right? And what is the use of principal components and what they actually mean, right? And we also seen that that works for the data set where we have that the data set lies in a linear subspace in any dimension, right? Or specifically, if I talk about if your data set in two-dimensional plane, a two-dimensional input space, then if there is a linear relationship between the features, then the principal components helps to find the most important directions, right? In which you can get the most variance of the data set where the data set has uh, the most importance, right? So those directions we try to find out using the principal component, and we have seen that how to find those principal components. We have seen the linear algebra behind that and how those things works to find the principal components. And in last, we have seen that those principal components are nothing but the eigenvectors, unit eigenvectors of the covariance matrix, centered covariance matrix. Center means where once you center your data set and find the covariance matrix, which is just XX transpose, then the eigenvalues of the covariance matrix gives you the principal component. That's what we have seen in PCA, right? But there are some issues with the PCA that we are going to solve in this particular session, right? So first issues with the PCA is the time complexity issues, and another is the non-linearity in the data set. So what is the time complexity issue? As we have seen that okay, so as we have seen that the principal components are the eigenvectors of the covariance matrix, then those and the convention that we are going to follow is the same that we have followed in the lectures. X is a data matrix of the dimension d cross n. So this covariance matrix will be of the shape d cross d. So this finding eigenvalues is of the order dq, and finding eigenvectors of this particular matrix will be a very tough task if your d is very great, d is very larger than n, or d is larger than n, right? In such cases, this becomes very complex equations to solve, or very computationally lengthy part to solve, right? Whenever you have large number of features, then the number of examples in the data set. So how to solve this issue? And the another issue is okay, so we'll talk about the second part later. So first solve this issue. So here we have seen the principal components that we are trying to find out are the eigenvectors of unit eigenvectors of the covariance matrix. Now we will choose the different path to find the same things, right? So our task is to find the eigenvectors, not the eigenvectors. Our task to find the principal components of the given data set, right? Now we are going to take the different route for the same thing. Right. For that, we are going to use some facts that we have discussed in the lectures. The very first fact is that the species or the principal components are the linear combination of the data points, and that easy to show as well, because we have we already know that those the WK are the principal components, K principal component. Then those principal components are the eigenvectors of the covariance matrix C, right? So this is your eigen equations, right? So this eigenequation says that the kth principal component will be the unit eigenvectors of the covariance matrix, and corresponding eigenvalues of the corresponding eigenvalue is the lambda k, right? So this is your kth eigenvalue or the kth principal component, right? If you write C equal to XC is your this XX transpose, right? 1 upon n XX transpose, and you can write it as XI transpose summation over all those vectors in a matrix form, right? And once you do this thing, this algebra, some bit of algebra here, you can get WK as this thing, right? So this you can see that the kth principal component is the linear combination of the all the data points. So this is from here you can see that all the principal components, any principal component as a linear combination of the data points. So if we know this coefficient, you are done, because ultimate task is to find the principal component, right? So if you know these coefficients, then your task is done, because you have data set already with you, right? But if you look at these coefficients here, you have values that we can find using C. That is okay. WK, but again, if you find WK, the coefficient itself contains the term WK, and we are finding WK. So coefficient itself contains WK. So directly we cannot find this coefficient. We have to choose a different way to find this coefficient, right? So if we have found this coefficient, then we have the eigen vectors or the principal components. These are principal components. Okay, the kth principal component.
Hello, sir. Sorry to interrupt. Can you do it little slower because it's hard to observe?
Okay,
Yeah.
the pace you are talking about, right?
Yeah.
Okay, I will try that.
Yeah. Thank you, sir.
Okay, so till this point, any doubt?
Sir,
Here I
yes, sir.
just introduced that what we are going to do
Sir, if
here.
you can explain from XI transpose,
Hmm?
I mean, how XI came out and XI transport, how it came, sir? Like,
Sorry, I didn't get your doubt.
sir, this is CWK equal to lambda K WK,
Hmm?
and covariance matrix is 1 by n X transpose.
It's just manipulation of the terms here. You put
Yeah,
C here as 1 by n
yes,
summation
sir.
over xi transpose
Into
uh,
WK.
wk. This is your
Yeah.
wk,
From
and here
here, the XI was inside the sigma, sir. How it came to the right side from left side? Here, XI transpose into WK. Okay, I can. It is come here,
hmm?
but after sigma summation, XI will come, no, sir. How that XI came to the right side of WK?
Okay, that thing. Okay, so you are saying that this xi transpose into wk, right? And why you can write it as xi transpose wk into xi, right? So if you look at this term, this is just a constant. So you can write it here and there, doesn't matter.
It will be just a dot product.
Yeah, so it's just a constant. So it doesn't matter if you write, I mean, it's just a scalar to multiply with the vector wk, xi here.
Okay. So
Okay.
only XI is a vector and XI transpose WK is
Wk will be a scalar quantity,
scalar.
right?
Okay. That's how, sir. Okay, sir. Thank
Okay.
you. I will see.
Sir, hello, sir.
Yeah.
How that WK come on the both sides, like is left hand side as well as right hand side?
Yeah, so that is the point here, right? So here I can see that wk is the linear combination of the data points. That point is clear. But inside the coefficient itself, you have wk, right? So we can not directly find this coefficient. For finding this coefficient, you have to find some different ways to find these alphas. I'm calling this alphas k. Okay, alpha k, alpha i's. Okay, and how to find it? That we are going to do next.
Okay.
Okay. So till this point, only thing I mentioned is that we are going to find the same principal components, but using the different route. Till in the week 1, we have seen that we have designed a covariance matrix, and then we have seen that those most important directions are nothing but your those eigenvectors of the covariance matrix, right? That we have seen in week 1. Now, for finding the same directions, same principal components, we are going to take the different route. Okay. So this fact says that your WK can be written as the linear combination of the data points, right? So X here is your matrix, right? So I'm very new to this writing device. So here you have n d cross n matrix, right? So each column is your data point. So here you have first data point x1 here, similarly x2 here, and up to n data points, right? So you have d cross n matrix, and if you multiply it by some alpha, so here if I call it alpha k1 up to alpha k2 up to alpha kn, right? So this is your alpha k. This is your alpha k. This is your x matrix. So here you can see that it is your alpha k1 x1, right, plus alpha k2 x2 This is your x2, and so your kth principal component is your linear combination of the data points x1, x2 up to xn, right? So this is what we have seen now. So I'm writing alpha wk as a linear combination of the data point. Now, how to find these alpha k's, right? So this is a vector of the dimension n, right? Right. So we have already seen that inside this alpha k, wk contains. So we cannot directly find this alpha k using this equation. So for finding that, we have done some of algebra. I'm skipping that part, and you can see in the lectures. It's very easy linear algebra, and you can see that those once you do that linear algebra, you will get these equations. What you can tell about this equation? This here k is your this matrix x transpose x. So what is the dimension of k here?
N into n.
N cross n, right? So if I talk about this equations, what can you say about this equation? Any specific things you noticed here about k?
Sir, again, this it's a matrix into a vector, and lambda n lambda will be the eigenvalues of the k.
So this is the eigen equation, right?
Eigen equation.
Right. So what are the eigen vectors here?
So
Yes.
alpha k.
Alpha k.
Alpha k are the eigen vectors, and what are the corresponding eigenvalues?
N
N
lambda k.
N lambda k. And where we have started we have seen that C is the covariance matrix which is xx transpose 1 by n xx transpose, right? And we have seen that kth, the largest kth eigen vector is alpha k, and corresponding eigenvalue is lambda k. And we have seen that this is again your eigenvectors of k matrix, which is x transpose x. Corresponding eigenvalues are n lambda k.
Wk, so not alpha k.
Sorry,
The eigenvector of C, it's Wk, right? Not alpha k.
alpha k. So yeah, wk, right? Yeah, wk. Sorry, wk and correspond. Yeah, sorry, this is not alpha k. The wk and corresponding eigenvalues are lambda k. Right? That's what we have seen. Right? Here again, we have seen that in the eigenequation of k, eigenvalues are n lambda k. Right? So here in the C, the eigenvalues were lambda 1 to lambda k. In the k, your eigenvalues are n lambda 1 up to n lambda k. Right? And there is one fact about the linear algebra that says that the non-zero eigenvalues of xx transpose and x transpose x, this is x transpose x, are same. Non-zero means if xx transpose have eigenvalues up to lambda 1 to lambda k, your the eigenvalues of x transpose x also gonna be lambda 1 to lambda k. Okay, that is a fact in the linear algebra. Not we are not going to prove this, but remember this: all the non-zeros eigenvalues are the same, and the remaining eigenvalues of the matrix which is of the larger size are zeros. Let's say this is of n cross. This is your n cross n. Sorry, d cross d. This is n cross n, and n is greater than d. In this case, this matrix will have large number of eigenvalues, more eigenvalues, and remaining eigenvalues will be zero, and all the non-zeros eigenvalues will be same. Okay, this is the fact that we are going to use here, right? So here we are finding alpha, and we have seen that these alpha are nothing but the eigen vectors of k matrix, and k is your x transpose x. But are those eigenvalues, those alphas, the same that we are trying to find? Because here we can see that for n eigenvalues n lambda k, alpha k should satisfy this equation, and this equation comes from the fact that your w transpose wk transpose wk should be 1. From this fact, we can see that this for that eigenvalues or eigenvector, this equation must be satisfied, right? And once this equation satisfied, this satisfied only when your alpha k is your these things, right? So I'll talk about this beta k. What is this beta k? So the algorithm says that first you find k matrix,
Sir,
which
one
is your
second, sir.
x transpose x.
Sir, one slide, two slide up. Can you go a little bit? Just wrote this k. No, sir. Where this k? No, this only. That only, sir. Previous one. Yeah, this equation you wrote, no, sir. X alpha k. I mean k into alpha. Below
Okay.
that, sir. You just go above, sir. I mean, you scroll down little bit. One more, little bit, sir.
This one.
This one.
Hmm?
Alpha alpha k transpose k into alpha k equal to 1. How this one came, sir?
This comes from this one, WK transpose WK, and you can use WK
No, okay,
or you
this
can use these equations.
these are
You,
all perpendicular WK transpose and
no,
WK.
we take the unique principal component, right?
Yeah,
The unique
that's
eigenvalues. Sorry,
yes,
unique eigenvectors.
sir. Yes, sir. Okay, and this k
K is your matrix X transpose X.
x transpose x is k, and alpha k transpose and alpha k. I mean, there are only two vectors in this W transpose k and WK equal to 1. There are only two things, sir.
Okay.
But here we have having three items, no, sir. Alpha k transpose and k, then alpha k.
Okay.
How I am not able to relate, sir.
So is it
Okay.
should be
So,
alpha k or it should be beta k? I think it should be beta k.
no, this is alpha K. So you want the proof of this?
Not proof, sir. From where it has come? From which equation this alpha k must satisfy the following equation came? So that one I just wanted to see, sir.
It's
If
WK,
possible.
we can write it as X into alpha K, and if we pre-multiply it with W transpose, we can get here.
Okay, so you can use this equation. So here we have seen that WK is nothing but the linear combination of the data points, right? That we are calling like this, and we are trying to find this alpha K, right?
Ah,
So
yes,
so,
sir.
so if you write WK transpose WK equal to 1 here, just put X alpha K here, right? So this will be your X alpha K transpose X alpha K, right?
Okay, okay.
Now, what will be this? This is alpha k transpose X transpose. This is X. This is alpha k equal to 1, right? What is this? This is we are calling as K,
Okay, okay. Okay, sir.
right? So we have seen that this alpha k is nothing but the eigenvectors of this K matrix. But which eigenvalues to take? That we have to determine, right? For finding the kth eigenvector or kth principal component, which eigenvector to take, that we have to determine. And this equation says that the eigenvector which satisfies this equation or equality, that eigenvector will become your kth principal component. I mean the coefficient to find the principal component, and you just put this alpha k here, then you will get the kth principal component. Okay, so alpha k is not the principal component here. This is the k, the eigenvector of k which satisfies this equation. Okay. Okay. So the your now your algorithm says that you just find the k matrix which is X transpose X, then find the do the eigen decompositions of k, and if the beta 1 up to beta l are the unit eigenvectors corresponding to these eigenvalues, right? These eigenvalues of k, then your alpha k is become beta k divided by square root of n lambda k. Because here we have seen that this, if you put so if I call beta 1 to beta k to be eigenvectors of k matrix corresponding to the eigenvectors n lambda 1 up to n lambda k, then we have seen that beta k should satisfy these equations. And if you put this beta k divided by n lambda k here, you can see that this equation satisfy this particular equality, and it in turn says that these alpha k's are the coefficient that we are trying to find out, right? And here you can directly say that so your algorithm says that find the k matrix first, find the eigenvectors. These are the eigenvectors corresponding to these eigenvalues n lambda 1 to n lambda l. So you just arrange this in the decreasing order and corresponding unit eigenvector. Then the coefficient alpha k will become beta k upon square root of the eigenvalues of k. This is the eigenvalues of k, right? The kth largest eigenvalue of that. Once you have alpha k, you have the kth principal component, right? This is the algorithm for finding the principal components, right? So initially, what we have seen in the week one, we have find C there, and we have directly says that the let's say their lambda 1 up to lambda k are the eigenvalues in the descending order. Then the unit eigenvectors, let's say those that will be W1 up to Wk, and those becomes your principal components, right? So these are the unit eigenvectors. But in this case, what we do, we find K first, which is your X transpose X. Then we find the eigenvectors corresponding to eigenvalues. Let's say eigenvalues are, and let's call them some other name. Let's call them mu1 up to mu k. So these are the eigenvalues in the decreasing order. And the corresponding eigenvectors, unit eigenvectors, let's call them beta 1 up to beta k. So these are the unit eigenvectors. Okay, and once you have unit eigenvectors, you just do alpha k will become your beta k divided by root over mu k, right? And your principal component wk will become x into alpha k. Right, so this is the algorithm for finding the eigenvectors, right? So here the issue has solved because for finding eigenvectors for C, the dimension goes d cross d here, and here your dimension is becomes n cross n. K is of the dimension n cross n, right? So n we are calling that d is greater than n. Then in this case, we have solved the issues of the time complexity. Okay.
Sir, but complexity will be O of cubic only, no, sir? Either d
It's
cube or
again a cube.
no.
It's again a cubic, so it becomes somewhat lesser if the d is
N
very
cube.
high. Then yeah.
And if d equal to n, this will not work. So we have to learn some
No,
other
so
algorithm.
in practice, we generally go through this this procedure only. We can avoid that one where we find the corresponding eigenvectors or the for the covariant matrix. So here this is of d square n actually, of not d cube. Then how this order comes, that I'm very not sure. This is for the d square n. Okay, or you can call it d cube in general. Okay, so
Sir, why is it under root n k and
hmm?
lambda k?
Sorry, why this is?
Why is it under root n lambda k instead of alpha k line?
Your voice is very faint. I'm not able to listen properly.
Sir, one
Sir, I'm
question, right?
saying
This n lambda, whenever we calculate eigenvectors, that eigenvalue that always be n lambda, right? Not lambda.
That you just what is your algorithm is that you just find the eigenvalues.
Okay, that
Let's call
eigenvalue is equivalent to n into lambda, right?
n lambda. Yeah.
Okay, so if there is any numerical, though, again we don't have to put n from
No,
the.
no, no. You just find the eigenvalues and divide it by the first find the eigenvalues and corresponding unit eigenvector.
Okay.
And
Okay.
for unit eigenvector, you divide it by the square root of the eigenvalue. That will become your alpha k.
Okay. 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 So this alpha k will be a one line matrix, right? In
Yeah,
n
this is of the shape n. I mean, this is will be in the dimension Rn.
Okay. Okay.
And once you take the linear combination with the data points, all n data points, you will get the kth principal component.
Okay, and this wk will always be linear combination of some xi's, and at the same
Not
time
some xi's, all the xi's.
all
Depending,
the
if,
xi's.
yeah,
Yeah.
if some of the values are zero in alpha k, then you can call that those data points is not contributing to finding those eigenvectors. That's all
Okay.
you can say. But all the wk's become the linear combination of the data points.
At the same time, all the xi's will also be the linear combination of wk, right?
Yeah, that we have seen in week one. Yeah, that is also correct statement.
Yeah, yeah, okay. Achha, sir, one thing I was, while doing the questions, I was facing some problem, right? So I was referring to previous year's recorded video. So I was seeing the September 22 videos, but the content was entirely different there. So
September 2022.
yeah, September 22, the week one content is entirely different than what we are studying in
Yeah,
right
the
now in
content
week.
was changed after that.
So do we have any recorded video after the content change?
Yeah, we have.
But I could not find, sir, there. I could only find the live session for September 22 only.
Okay, I'll share one Google Sheet. There you can find the list of all the slides or all the recorded videos.
Okay, so where you will share that, sir?
do one thing. You just paste on the discourse and you tag me there.
Okay, I have never used Discord, sir, before. I'm sorry, but
You just go to discourse and write in the MLT course channel.
okay, okay, I will do that. I will do that. Yeah, thank you, sir.
Sir, one basic query, like how we understand is any given vector can be expressed in terms of their eigenvectors, right? But here you are saying that WK is x lambda k.
Hmm.
So how is this
X
true?
alpha K.
Yeah, WK is x alpha k. Yeah, correct.
Hmm. Yeah.
So how we are expressing eigenvector now in form of given data?
Okay. So
Mhm.
you want that theoretical proof or geometrical one you want?
I mean
Geometrical I
anything.
cannot show here because
Uh-huh.
to design a data set and then find the eigenvectors or the principal component, then we have to show the eigenvector. These principal components are nothing but your eigen linear combination of the data points. I've never done this, but theoretical we have seen that, right? These WKs become the linear combination of the data points. That
Correct.
proof we have seen, but geometrically I have to check whether we have some videos on that or not. But
Okay.
yeah, yeah, correct. Your doubt is correct. To
Okay.
see some geometrical proof of that.
Yes. Okay. Anyways, if you have some videos, that will be really helpful. I'll put this
Yeah,
on discourse also.
yeah, correct.
Okay.
Sir, I have
But
one
this
doubt.
theoretical proof is clear, right? This how these WKs become the linear combination of the data points.
Not very clear, sir. If you can
So
just.
this
It's
comes
not
from
clear,
the
sir.
fact you just little bit manipulations of this equations.
Okay.
Where is that? Uh, this one, right? We have seen that this alpha WK we are calling as the linear unit eigenvectors of C matrix, right? Here C
Yes.
you put as this 1 by n xi transpose WK, and here you can say that WK becomes the summation over these alpha ki's and xi's, right? So sum over all
Okay.
the data points. So all WKs become the linear combination of those data points xi's.
Oh, okay. Got it, sir.
From here, you can see that WKs are the linear combination of the data points.
Okay. Thank you, sir.
Sir, the statement is like WK is the linear combination of the data points,
Hmm?
but the other statement is like the XI is the linear combination of each WK.
WK, yeah, correct.
So how that is happening? I didn't get that.
That we have already seen in week one,
Uh,
right? And that is how you find your WKs, those principal components. You started with saying that we are finding the most important directions, and we project all those data points on the principal components and then find those directions, right?
okay, but in week one, where did we get this remark? Like, can you
Uh,
explain this?
Week one, I'm pretty sure it is in week one. Which video that I'm not sure. What
Are
is
you
in week?
talking about the remark that we get when we said that when we sum up all the uh, WKs, then projection of all the XIs on the WK that will be equal to zero. That you want to say?
No, 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 no. Right, I'm not talking about. Not sure about the specific time stamp, but probably in the week 1.3 you will see that. I have to check the slide, but that's I'm pretty sure it's in week one.
Sir, can you please explain that now?
Which
I'm
part?
sure. So the same thing which he's asking, Himanshu.
Okay,
So
then we have
this,
to go through the entire linear algebra part of that because sir has started with designing the eigenequation. I mean that.
sir,
Uh,
maybe in short, you if you explain it, maybe we will
okay, let
follow.
me open the slides first, then I'll explain. Give me 1 minute. Can someone be share the folder where we have all the slides? I don't have access to that folder. You must have on the portal.
Sir?
You have access to the slides, right? All the big slides. Can you give me the
Yeah,
link of that folder?
I will just share it, sir. Now, you want to share the folder
Folder link, yeah.
link? Okay.
Or I got it, I think. No, this is Week 10.
Sir, I have posted it in the chat.
Yeah.
It's
Okay, Week 1.
last one, sir.
Yeah. I just point out where this proof has been done. Give me 1 minute.
So which proof are you looking for, sir?
The data points are the linear combination of the principal components, right?
So it's in second week.
No, that is about okay. So
On the 17th page.
correct. Right. So here in a specific dimension that we have in particular dimension, that d dimension, we are saying that all xi's become these things, right? So xi transpose w, this is the projections of the xi data points on the first principal component times this eigenvectors, right? This principal component. Similarly, this is your xi transpose w to w2. This is the projection of the data points on the second dimension or the second principal component times this directions, right? And all those up to d directions, d principal components, we first take the projections and then take the directions, right? So this exercise becomes a linear combination of all the principal components that we have seen in week 1. So here you can see that all the exercise are the linear combination of the principal components, and that is true for any dimensional space. Let's say you have only Cartesian space where you have only x and y dimensions, and if you take any data point, you can write it as a linear combination of x and y, right? We are just finding the different dimensions, different directions where those directions capture the most important features of most important information of the data set. That's it. That's what we are doing, right? So in short, if I say, you must have seen those things like basis, how basis used to find linear combinations. I mean, to take linear combinations to find any data points, right? That you must have seen. So in short, if I say, let's say you have any space, let's say two-dimensional space, xy plane, and the Cartesian space xy, right? So x and y. Here, if you take any data points, let's say I take 3 in 3, 10. So this you can write as, this data points can be write as 3 projections into x direction, which is your 3, and here it's in the y direction you take projection which is 10, and you can write it as 3 plus 3 into x direction unit vector plus 10 y direction unit vector, right? So this is your 3 in the 3 projections on the x direction and 10 projections on the y directions. So similarly, you can write any data points. You can write is that linear combination of these two directions. So what we are doing in the principal components, we are trying just finding, let's say you have all these data points, right? So these are your data points, right? So all data, these are your x plane or w plane. What we are doing, we are finding it directions, these directions. This becomes your w1, and this becomes your w2, right? So in this directions, you have the most important information about the data set, right? And in this direction, this is the next important directions in which you have the most important directions or the information of the data set. So here what we do for so you just think like just rotating the plane, or say shrinking or rotating the plane. So here what's happening is for this, if you want to represent this data points using w1 and w2, you just take the projections here, projection here, right? So this is your projections of this data point on w1. This become your w1 transpose xi, right? And in this directions you have unit vector which is w1, right? So this is the component in at w1 directions, and similarly this is your component into w2 direction. So xi you can write as w1 transpose xi, w1 plus w2 transpose xi into w2. So this is the component the w1 direction, this is the component into w2 direction. So any data points can be written as a linear combinations of the principal components. This is the basic facts of the linear algebra, right? That we have seen in week 1. Here we are saying that wk becomes the linear combination of the data points.
Sir, how is alpha k equal to beta k by root n? Can you
So
explain
here
that?
we are not saying that we want we here we are seeing that the alpha k that we are trying to find out must are the eigen vectors of k matrix that we have seen, right?
Yeah, yeah.
But at the same time, we are saying that this alpha k must satisfy this equation. Alpha k transpose k alpha k should be 1, right? So which eigen,
Yeah.
you know that if let's say for any matrix A, if let's say mu1 is the eigenvector, then 2 mu1 will also be eigenvector, right? 3 mu1 is also eigenvector. So any constant times, let's say k mu k is also eigenvector, right? So out of these, which one to choose, that gives me the real alpha k, that coefficient that we are trying to find out, right? So out of all those things, choose the that alpha k which satisfies this equation, right?
Okay. Yeah.
Okay, and we have seen that using this fact that wk transpose wk should be 1, using this fact where we have write that these things, using this fact we've seen that those are nothing but just take the unit eigenvector which we are calling as beta k, and then divided by root over lambda k or n lambda k, right? This becomes your alpha k that we are trying to find out. This is your unique eigenvector, this is your corresponding eigenvalue. Okay,
Okay, sir. Okay, thank you.
so algorithm is simple enough. You just find the k matrix which is x transpose x. Okay, find the eigenvalues, which is your, let's say, mu1 up to mu k. This is in your decreasing order. Corresponding eigenvalues, unit eigenvalues. Remember, this is the unit eigenvectors, which is your beta 1 up to beta k. Right? So these are your unique eigenvectors. What will become your alpha 1? This is your beta 1 divided by root over mu 1. What will be your alpha 2? This will become beta 2 divided by root over mu 2. Similarly, if you find kth principal, the coefficient which will be alpha k, which is your beta k divided by root over mu k, right? So this is the unit eigenvector. This is the corresponding eigenvalues, right? So what will be your first principal component w1? This is x alpha 1. What is the kth principal component? That will become x alpha k, right? The simple enough. You just find k, find the unit eigenvectors, corresponding eigenvalues, and then just take alpha k as beta 1 root over square root of eigenvalues, right? So this will becomes your alpha k's. And this solves the problem of time complexity. Okay. Okay, let's move to the next part, which is more essential here and most important for week 2. And it is says that data need not to lie in the any linear service space, right? And that is true in the most of the real world data sets. Your data set need not to be linearly related. Let's say if you have features x1, x2, x1, x2. Once we have find eigenvector, we say that those lies any linear service space, right? What if your data set is like something like that? Your data points is following this relationship. Can you find the most important directions? Yeah, here you can say that this becomes your most important direction. This becomes your next most important directions. Here, what will be your most important directions? You cannot find because the data set is not linearly related, right? So it doesn't lie in a linear service space, right? So what to do in such cases? So the idea is that we sends all the data points in the higher space, higher dimensional space, such that in that higher dimensional size space, your data points lie in a linear service space. Okay. So what is the idea? If your data points lies in, let's say this is your data set, right? You send into higher dimension, let's say 3 dimension. In the 3 dimension, it is not possible. Actually, it goes into 6 dimensional space. Let's assume just assume it's not true. You send this into higher dimension. Let's say in this case, you send it into a 3 dimensional space where it lies on a plane, right? And plane becomes a linear service space of the three-dimensional space, right? So the idea is that you send all the data points into higher dimensional space such that in the higher dimensional space, the data points lie in a linear service space. Okay. And once you have data set which are linearly related, you can apply the principal components algorithm that we have already seen, right? So only issue is that your data set doesn't follows linear relationship, right? So for example, let's say the features are f1, f2, and your features follows this relationship. What is this? This is the equations of a circle, right? And so data points are coming from this equations, right? So here it doesn't follow a linear equations. What if I here your features are f1 and f2? What if I send them into f1 square, f2 square, f1, f2, and f1, f2, and 1? If I take these directions rather than these directions, in this directions or in this space, my relationships become linear, right? In this input space, you have two-dimensional relationship or the quadratic relationship. But if your dimension itself are f1 square, f2 square, in this case, this becomes linear equations, right? So idea is that I sense the data points into higher dimensions, such that your given data sets follows the linear relationship. Okay. So here I'm sending the data points from this space to this space, and you have already seen linear transformations, right? How we take the linear transformations from one space to another space. Okay, and the proof is why we are calling that the data points lie in a linear service space, because this equations holds for every equations, right? So in the let's say in d dimension space, your data points are x1 up to xn and data points. Once you apply it linear transformation phi, that phi sends the space d to capital D, right? Now your higher dimension space has dimension capital D, right? So in the higher dimension space, your data will become x1 will become phi x1, right? And x2 will become phi of x2, right? And and the data points will become phi of xn. Now these data points phi x1 to phi xn follows linear equations or linear relationships, right? And why this is true? Because there is one vector for which this equation is true for all I, right? For all data points, there is one vector which follows this equation. It means that this data points is orthogonal to all the data points, all the data points, right? It means that this all those xi's phi of xi's lies in a linear subspace. It is or just think like you have a 3D space, right? 3D plane. You have dimension x1, x2, x3. Now in take any plane, right? If I take this plane, there you must find a directions mu for which this becomes orthogonal to all the data points, right? So you can think something like this. So if you are able to find one directions for which this is orthogonal to all the data points, then all those data points lies in a linear subspace, right? So for the three-dimensional space, plane is a linear subspace that passes through origin, right? So now our task is to find this phi. Once we have this phi, which sends the data points into higher dimension such that all the data points follows linear relationship, we are done. Because in the higher dimension, we can apply now our original algorithm that we have already seen, right? So now this phi of x1, phi of xn, these are my data points into higher dimension space. And we have seen that those follows all live in a linear subspace. Then now we can apply PCs on those data points. And how first remember we have to we need not to center, because remember for finding k and for finding c, we first center the data points and then apply the algorithm. But here we need not to center the data points, or we have to center, but if xi's are center, phi of xi's need not to be centered. That you can remember, right? So, or you can take some example. Let's say you have some data points which are in the one dimension space, which are your xi's, and if I take phi of xi as let's say xi square, right? So in this case, your data points, let's say minus 1 1, right? So this is the center data point. But in the case of phi of x1 will become 1 and phi of x2 will become 1. So these are not centered, mean centered, right? So you can see that these, if phi xi are centered, phi of xi need not to be centered. Okay. So once we have this phi, we can transform all the data point to higher space and then can apply PCs. But this is not a right way, because this finding phi is a tricky part. Okay, so there is a trick, and that trick says that, and for that trick we use the kernel methods, right? So for coming to that trick, we first define the kernel function. And the kernel function, what it does, it takes all the input from the original space, and the output of that function is such that it's the same as phi x transpose phi x a, right? So it's take any two inputs. If you operate upon k, the output is the same as phi x transpose phi x a, and ultimately we need these things, because if we apply PCs on these data points, you remember we have to find k, and for k matrix, it is your phi of x transpose phi of x, right? Because your data points of data set is phi of x, right? Now, so for k matrix, you need these things, right? Once you have these things, you can find the eigenvalues or eigenvectors, and you can find the or you can find the principal component. So for short trick, you just add a kernel function. You need not to have the phi itself. If you have kernel function for finding these things, you can just give the input xi exists to function, and you are done, because this output will be same as these things, right? So for finding k here, you just take k xi xa, right? The ijth element will become, just take the ith data point, jth data points, put in the function, take the values and put at the ijth place. That will become that will give you the k matrix, right? So this is the short trick. So how to find this kernel? And the fact is that for any valid transformation, you can find a kernel function. And to check whether a function is valid or not, you just if you are able to find it appropriate mapping phi, then you can say that the given function is a valid kernel. Otherwise, there is another way. You have to check these two conditions. The condition says that the function should be symmetric. It means that for any data point, k xi xj should be similar to k xj xi, right? So let's say you have k something like let's say you have r2 cross r2 to r, right? And the functions is something like that: xi xj equal to x1 square, or say x something like some r2 to r2, some function, or say let's say you have x1 as uh, x1 by x1 x2, and by one as by one by 2, right? And you define the function kx1 by 1 as x1 by 1 plus x2 by 2. Is this symmetric, right? Let's if
So
you take,
basically, we can say the dot product is commutative. That's
yeah. So in this case, if you find k by 1 x1, it will become something like that, right? So here in this case, k x1 x1 by 1 is same as k by 1 x1, right? So this is symmetric for all the data points. And the second condition is that you find the this K matrix for which this should be positive semi-definite. Positive semi-definite means all the eigenvalues must be non-negative. Okay, if these two conditions satisfy, you can call that function to be valid kernel, right? So something like that. Let's say, for example, let's say some function you can take. Let's say I define a function like k function from, let's say, R2 to R2 to R, and the function says that for it operate upon two data points. Let's say x on y, and it's something like that where x is your, again, x and y are in the two-dimensional space R2, and x I'm taking as x1 x2, and y I'm taking as y1 y2, and I'm defining the function as, let's say, x1 cube by 1 plus x2 square by 2 square. Is this function valid kernel?
No, sir.
Why?
Sir, if we do the dot product, it won't be commutative.
I'm not doing dot product. I'm just checking whether this function is valid kernel or not.
Sir,
No, but
if
it has to
we
go to R2.
So it's
R2
metric.
It's not symmetric, because if you find a k by x, then in this case, what will be the here? What will the output here? It is just
So y1 cube x1.
y1 cube x1 plus x2 square by 2, or by 2 square x2 square, right? So these are two not,
Yes.
these two are not same. So here this k x by is not same as k by x, right? So this is not symmetric.
Sir, is this not K from R2 to R2 cross R2 to
Yeah,
R,
this
no?
is this is R. Yeah, correct. Right. So since this doesn't follow the very first condition, which is symmetricity, so this cannot be a valid kernel. This cannot be a valid kernel for any transformation, for any, or for a transformation. Okay. What if I say x1 cube by 1 cube? Now this is symmetric.
Then it will be valid, sir.
So then metric.
It is symmetric, but we have to check the second condition as well.
Mhm.
So I don't prefer going to that way, because finding eigenvalues, again, a tricky task. Then you have to find the k matrix and all the data points. You have to find kernel function, then find the eigenvalues and everything you have to do. You just try to find out a valid matrix here, or valid transformation here. So transformation, you have to find phi from R2 to some higher dimension R D. I'm not sure which one, for such that k x y is become phi of x transpose phi of y, right? Such phi I need to find, right? So here, if I in this case, if I look at something like phi of x as, or I can say that this is your x1 cube by 1 cube, right? X1 x2 square by 2 square, right? So this is just x1 cube or x2 square multiply by with by 1 cube by 2 square, right? This dot product is same as this thing, right?
Yes, sir.
Right. So this is this I can call it phi of x, and this is transpose, and this is I can call it phi of y, right? So what is your phi? Phi become, phi takes any data point x and sends, or your data points is your x1 x1 x2, and this sends to, again, two-dimensional space, which is your x1 cube x2 square, right? So this is sending from R2 to R2 again, but it takes this transformation where your dimension was x1 x2, now your dimension are x1 cube x2 cube, right? And you can check these conditions hold for any data points. Once you have this phi, you can call this function to be valid kernel.
Sir, but we should be able to find that matrix x and y, no, sir, like x cube x square, y cube y square, we found out. Like that, it has to be easily convertible into matrix dot products if you want to take.
Okay, then.
No, what I'm trying to understand is x1 cube y1 cube plus x2 square y2 square. This is nothing but x1 cube y2 square dot with y1 cube y2 square. Correct, no, sir?
Yeah, that's what I've done here, right? So
Yeah,
that's what I've done here. This is the
yeah,
dot
you have
product of
done
this.
that. I understand, sir. I understood.
Hmm.
But for any other or expression, if you get instead of that x1 cube y1 cube plus x2 square y2 square,
Hmm.
how from that expression we can make it as dot product?
That you have to think of, right? Let's say I give you something like that. Give me some valid transformation. Let's say. Uh, uh, okay, let me first design a question transformation, then I'll come to that part. Okay, otherwise I will end up with giving you the answer only. Okay, so I'm stopping the presentation here. Okay.
Now we can take any other already like quiz questions or somewhere where it this particular operation was carried out, and where we can see another.
Just give me 1 minute.
Sure, sir. Thank you.
Okay, so okay, let me share it again. Okay, let's say you have a given function kernel which is R2 to R2 plus R2 to R, and the kernel operates on two data points, which is your x again x1 x1 x2 in two-dimensional space, and again by as by1 by2 on the two-dimensional space. And if you operate upon x1 and x2, this kernel xy, and then it's give as x1 square y1 square plus x by plus let's say constant 6. Okay, now can you find the phi here, valid phi? So phi sends your data points from R2 to some dimensional space, right? I don't know which d. Right, it takes any data point. Let's say it take x, which is your x1 x2.
I think we can find f1 square, f2.
So can you give me that that
x1
standing?
square, x1 root 6.
Root
X1 square, x1.
x1 root 6.
Correct.
Then y1 square, y1 root 6.
This is the mapping, right? This sends here.
yeah, one.
So this is
Yeah,
your
and
three-dimensional
correct.
space.
And phi of y1, y2 will be
Yeah, right. So here you can see that phi x transpose phi of y is same as kxy, right? So this becomes your valid kernel because you can find such phi here. Once you have a phi, you can call it a valid kernel.
To find out like this, then each and every combination like x1 square y1 square, the plus if you take only x1 square y1 square, that particular aspect either should contain both x and y, or it can be a constant.
Now you have to think of that. Let's say if I remove by here and my kernel function is something like that. Now you can easily say that this is not gonna be a symmetric one.
Yes, sir.
Right? Because if you write k by x here will become by 1 rather than x1, and this will become x1 square by 1 square plus by 1 plus 6. So these are not the same. So the function itself is not symmetric. So
Yes,
if
sir.
the first condition is not satisfied, your kernel need not to will not become a valid kernel,
Yeah.
right?
Yes, sir. The observation is each and every in the expression, each and every part where we are going to submit, each and every one should contain x and y, and that too in same power.
Then only you can say, but not, it's not a hard rule, but I mean it satisfies the very first conditions of being symmetricity, right? If whatever you are saying, if it's not holding, then it fails the very first condition of the symmetricity. Once it fails the very first condition, you need not to go to check a second condition, right?
Correct, sir. Correct. Then
Right?
just
So that is
observe.
observation, that is the correct observation, but that is not the sufficient condition.
Okay.
Okay, that need not to be sufficient one, but that is necessary. That's all you can say.
Sir, by looking this, how can we say that the k will be semi-definite?
Yeah, that's what I'm saying here. So if you have find phi, then you need not to check the go for the second way. The second way is that you have to check both the conditions, symmetricity and the positive semi-definite one, right?
We
So
can find
rather than going to the second path, you just you try to find a valid phi. If you are able to find valid phi, then you are done. You need not to check the
And we
symmetricity
don't need
and
to check this the semi-definite part.
semi-definite.
It
Yeah.
will automatically be semi-definite.
Yeah.
I think.
That is two different ways to check the validity of a kernel.
Okay.
The very one is that you find a valid phi, otherwise you go to check both the conditions. Okay.
Okay.
Okay, there are many questions in the practice and not many. I mean, some questions on the practice assignment or the last year question papers. You can go and check. It's not very hard to check the validity of a kernel function.
Yeah, it's not hard.
Okay. Okay.
So one more thing here. In lectures, the professor has mentioned, and when we transform the data points, suppose small d dimension data point, we transform to capital D dimension data point, right? So we can find the capital D there. Sir has mentioned a formula or just a remark like summation DCI I from
Okay,
I.
I remember that. That is only when we take the only I mean the combinations of the different features, not all the powers. We avoid the powers there.
Yeah, because it did not come out to be the same when we expand
Yeah,
that
correct,
solution.
correct. That sir, I think forgets to mention that it only takes the combinations of different
Combinations
features
only. It won't take the
or the
powers.
pairs of different features.
Yeah.
It doesn't count for the powers there.
So, sir, is there any formula, direct formula, or we
There is
have to make all the combinations in the exams?
there is a direct formula, but I that you have to do some permutations combinations to get that formula. Okay. I posted that on discourse previous to previous term. Uh, I can direct you to that link,
Yes, please.
Yes,
but
sir,
here I'm
please.
not using my own PC, so I cannot log into discourse.
Okay,
So
so then we'll put a
could
question, then maybe you can send the link over
yeah.
there in
So
discourse.
do one thing. You just check your discourse last term, not last term, last to last term. There is post on finding the how many. I mean, what will be the dimensions of the higher space?
Okay, I
Okay,
will
sir.
check, sir.
Yeah, so you'll
Okay, sir.
get a post, a big post, and some student has posted a proof of that as well.
Okay, sir. Thank you.
Okay. Okay. So and that is true only for the polynomial transformation, not for other kernels, right? So standard kernels are one is polynomial kernel, which is your polynomial transformation for which your let's say your transformation is polynomial transformation of degree p. Then your kernel functions which is operate upon x1 x2. It is just x1 transpose x2 plus 1 raised to power p. Okay. So yeah, and for this is for the mapping polynomial transformations of degree p. Okay, there is a standard one which is your RBF kernel, radial basis function kernel, all is generally called Gaussian kernel. Okay, and for this it sends into the it's operate upon two data points x1 x2, and it is like exponential x1 minus x2 square norm 2 square upon 2 sigma square, right? So sigma is the parameter of this kernel function, and this is called your Gaussian kernel. Okay, this sends your input space into the infinite dimensional space, right? So that's two you can remember. There are many other, but these two are the standard one. Okay. Okay, so come to the original issue where we are trying to find out the principal components, and what we have done till now. We have sent our data point into higher dimensions and saying that in the higher dimensions, these data points live into linear subspace, right? And we apply on the now PCs on principal component algorithm on our higher dimension space, right? So for that, you have to find the K matrix. For K matrix, your element contains something like that, right? So rather than finding phi, if I have corresponding kernel functions, I can make use of that to find K. Once I have K, I have done, because I can apply my principal component algorithm that we have already seen, right? But remember that we haven't centered our data set, right? Because we are calling that if I xi up to xn are centered, phi of x1 up to xn, phi of xn need not to be centered, right? So this need not to be centered. For centering this, this particular steps takes care of the centering of the data set, and the proof is given in the lectures. I'm skipping that part. You find k and use this algorithm and get the kc, and then apply the pc algorithm on this kc, right? So this is simple. K I is your matrix of the shape n cross n with all the entries as 1 by n, right? And you do this matrix, just solve the symmetric equations and then get kc. Once you have kc, you find the eigenvalues with eigenvalues as n lambda 1 up to n lambda l in the decreasing order, corresponding unit eigenvectors, right? Is the beta 1 up to beta l. That's the algorithm that we have seen before. Find the principal this coefficient, which is unit eigenvector divided by corresponding eigenvalues, and you get, once you have alpha k, you just wk will become your phi x, the data points, the linear combinations of the data points, right, which is your phi of x into alpha k, right? So for finding the principal component itself, you need phi. And till this point, we are skipping the finding phi, right? So for finding the wk, the principal components, you actually need phi, right? So we actually avoid finding wk principal components. What we do, we just find the projection of each data points, right? So for ith data points, your projection is phi of xi. Now, what will be the transformations of this data point into the principal component, k principal component? Is just phi of xi transpose wk, right? And here you can say that wk as, if you put wk as phi of x into phi of what is alpha k here, and do the manipulations here, this is your phi of xi transpose. You can see that this is nothing but this thing, right? Because from there you can get phi of xi transpose, phi of x j, and this thing you will get, and this will become k of xi xj. And you can say that the for projection of the I data point of k principal component is the same as this thing, right? And this particular term gives the how much these data points are similar, and this gives how much this coefficient give the how much weightage to give to those data points, right, or to that ith data point, right? So these things you can get, and you can do some numericals based on this.
Sir, can you scroll a bit? Yeah, this summation part, what does it make? Like, is it phi of xi?
This is the this thing.
Yeah.
This is the projections of the ith data point on the kth principal component.
So the question, my question is, why we are finding the projection here?
Because we don't have actual principal components. But what we have is the projection of the data points on the kth principal component. Because for finding principal components itself, you need the excess of the phi. And that we are avoiding to find phi, right? Because we are taking the short trick to by making use of the kernel functions, right? We are avoiding finding phi.
But again, we don't
transforming
have
the data point from one space to higher space and then apply PCs become more complex. So we make use of the kernel functions, and then we'll get those alpha k's. Once we have alpha k, we can find wk by using this thing. But here you
we
need
don't
phi.
have that, right?
We don't have phi, right?
So, but
but if you have phi, then you can find the principal components.
But here we don't have wk, right? So how can we find the
yeah, so here just do some manipulation. Wk you can write as wk you can write as phi x in phi x into alpha k, right?
Wk is x alpha k, right, sir?
No, we are applying PC on the higher space.
Okay. So phi
your
of x,
data points is your phi of x, not x.
Yes. Okay. Yeah.
Because your now data set is phi of x, not x itself.
But
The mapped one.
But when like when we find the projection, how will that make sense? Like we will have the projection. We don't have the
Directions.
component, right?
Yeah. We don't have the directions, but we have the in this directions. I mean, in this principal component, this data point have this much projections. That's all we have.
So we can find only that. We don't.
Projections, yeah.
Oh.
Until and unless if we have access to the phi, then you can find the phi itself, phi also.
Yeah, if we can compute that phi, then we can get the direction also. But if it's better to have something than nothing.
Yeah, correct. So these WKs are now can have dimensions more than the original direction D, right? Because now we have sent the data point to higher dimension. Initially, you have D-dimensional space RD. Now, phi, what does phi do? It sends your data points into capital D dimensions, right? So your K matrix will become of the shape n cross n, but your if you find C matrix here, it become D cross D, right? So it has more than D eigenvectors, right? More than D eigenvectors, right? So it may have more than D eigen principal components. The originally you have only D dimensions, right? And your that is possible when you have when you apply kernel PCA. Okay.
Okay, sir.
So can we do any numericals related to this?
Okay. Okay.
For example.
You have done questions on the practice assignment.
Yeah.
But here, can you paste the questions to me?
Practice assignment questions.
Or give me the link of the portal. I'm not sure whether I can access using this particular ID.
Okay, 1 second, sir.
Or give me the link right here in this particular folder. You have all the assignment as well, right? The solutions.
You want, sir, actually they have not uploaded the solutions of practice assignments.
It is there.
Neither
I
week
can
1
see
nor
that.
week 2.
I can see it here.
You can see here. No. Which one, sir?
Okay. Take one question here. Question number.
Sir, once again, where do you see this solutions PDF?
In the same folder, someone has given me the link of right.
Narendra. Okay.
In the same master folder, I can find the solutions as well. Or you probably may not have the access because I'm using the course ID. Which question is there for finding this?
So the link that is posted is the PA week 2 link. Practice assignment week 2 link. Questions. But we are not able to, I don't know, I didn't find the solutions PDF. I don't know about others.
The other link which I sent for the lecture slides, in that mock solutions are there, quiz 2 mock solutions.
We don't have any questions on finding these projections in practice assignment. Or I'm using some different questions. Or probably it is in the graded assignment. So it is in the graded assignment. When is the deadline for the graded assignment?
Sir, 4th, day after tomorrow.
Sunday, okay.
Yes, sir. PA solutions of week 1 and week 2 are not uploaded in the portal.
Okay, let's do one thing. I just give it toy data set and mapping and then find this projections. Okay. We don't have any questions in the practice assignment, but we can find a question here. Okay.
Okay, sir.
Sir, in that I have one question. Like now we just discussed. We have the projections, but how that makes sense for that data point? Like what preferences we can.
Okay, those projections you cannot do much because you don't have the directions. What you have is that this data point have this much importance in the very first directions. That's what you can find, but you don't know in which directions these projections are until
So,
and unless you have the
but can you give
mapping.
any real life example when this projection will help us to find some
Yes,
references
sir. I'm also not
inferences?
getting like why we are doing that, like how it will help in real life. I cannot correlate.
We don't have the direction, then it doesn't make sense to do all this, right? So,
We don't have directions, but projections is all we need, right?
how that make how that help us
Okay,
projection?
so there was one uh, not TSSN. Okay, let me check that link. There it was mentioned that those principal directions, I mean those projections will help you to find out.
I remember sir has used one statement that it help us in the
In the
regression problems. I think that's
no,
what sir
that is
has.
different. Yeah, kernel regression we will use, but here we don't. Where there we don't use principal components at all. That is a different part.
Not principal component, the projection we use.
Yeah, projections we use in the kernel regression as well. But that are not projections on the principal component. Or that projection that is different thing. We'll talk in week 5 there. So there is one sessions happened by the last term's TAs. I don't. Let me check the link. There they have given one examples where they use the projections to give the view of, I mean, how those can be used to find the linear higher dimension subspace. So visualization is not easy because here if you send two-dimensional space into higher dimension space, it directly goes to the six-dimensional space even by the two-degree polynomial transformations, right? So in visualization is not easy part. Okay, it hasn't been. No, I don't have access to this portal. I'm not added as a student here.
Where did you post the link that you are sharing?
Hmm?
The video that.
Sir, can I post you the same question on Discourse, tagging you?
Which question?
Sir, you are about to share a link, right? But you
Yeah,
couldn't.
but that is not public till now.
Oh, okay.
Okay, so let's do first this particular question, then we'll go to that. Okay, I'll find some examples where these projections will have. Okay, so here we were talking about how to make use of examples. Let's take a very simple example. Let's say your data set is this one. The dimension is, let's say you have t cross n, right? So you have, let's say, 3 cross 4. So d is 3, n is 4. 4 examples you have. Let's say your examples are 1 0. I'm just creating an example, maybe wrong. 102, 204, 111, or 212. So you have 4 examples. This is not working fine. So you have 3-dimensional space, right? So you have 3-dimensional space, and you have 4 examples. Now you apply polynomial transformation of degree 2, right? So what is the kernel value? Kernel of x, any two data point xi, xj. What will be the kernel function?
x1 transpose x2 plus 1 the whole square.
So this will become your x1 transpose x, or the xi transpose xa plus 1 raised to power 2. This is the kernel corresponding to 2-degree polynomial transformation. Okay. Now let's say you have to find those alpha k. So how you will find alpha k? What is the dimension of alpha k first?
Dimension of alpha k will be 4 cross 1. I think.
Yeah, this is 4 cross 1, right? This is a vector of 4 cross 1. Now let's say you have alpha 1, alpha 2, and alpha 3 and alpha 4, right? So all those belong into 4-dimensional space.
For this alpha k, we have to find the beta k for
yeah. So how to find this alpha k? What is the algorithm? First, you have to
we
find
have to
k.
find the k.
What is the ith element of k matrix?
We'll have to find with every vector.
Yeah. So this is kernel function xi xj, and this is ith element, and this will become, what is the dimension of capital K?
It
The
will
matrix
be 4 cross 4.
n cross n, 4 cross n, right? So the very first element will be k x1 x1, right?
Yeah.
What is k x1 x1?
It will be 1 2 3.
Right. So x1 is your this data point. X1 is your 102, right? If I put x1 here, x1 here, this will become x1 transpose x2. So this is 102 102 plus 1 raised to power 2, right? What is this? This is 1 1 4 5 6 36.
36.
Right. So the very first element of k will be 36. What will be the second element? What will be the second element? This will be k.
Can you show the data points also?
No, so just give me in terms of notations. This is x2 x1, right?
X2 x.
What is x2? X2 is this 204. So k
121, sir.
This is 204 102 and plus 1 raised to power 2. This is 2 8 10 11 11 square 121, right?
Yeah.
Similarly, you have here, you can find here for all those k matrix. Once you have 4 cross 4 matrix, right? You have to find for alpha k, you have to find eigenvalues, eigenvectors. Let's say your eigenvalues are lambda 1 up to lambda 3. You have 3 eigenvalues, let's say. Corresponding eigenvectors are, let's call them beta 1 up to beta 3. These are your corresponding unit eigenvectors, okay? So what will be your alpha k, or alpha? What will be your alpha 1? This is lambda 1 divided by beta 1 divided by root over lambda 1. Alpha 2
Sir,
will
should we find eigenvalues for this k matrix?
Yeah,
I think we have to center this, right? First.
Oh, data point centered. Oh,
Yeah.
okay.
Didn't center.
Yeah. So the k here you have to find kc. Kc will become k minus in k minus k in plus I n k I. Right. So here in will become a matrix with all entries 1 by n, 1 by 4, 1 by 4, 1 by 4, 1 by 4, all those entries. Okay. Now you have to find kc. It's a very lengthy process, right? Once you have find
Yes,
kc,
sir.
then you have to find eigenvalues of kc, not k.
Okay.
Okay. So let's say this alpha you can find, because here I cannot solve k 4 matrix to find the eigenvectors or eigenvalues, right? Manually it's not doable. Okay. So let's say your alpha 1 comes as let's say this 4141, something like that. Okay. So what is your W1 actually? W1 is your phi of x1 into alpha 1. Okay, phi of x1, where you have phi, you need excess of phi. but we don't know phi here. It's what we know is the two-dimensional, two-degree polynomial transformations, right? So what we can find that let's say I have to find the projection of third data point. Let's say third data point on first principal component W1. What will be that? That will be your K x3, or you have to multiply with all xi and alpha 1i summation I over 1 to 4. Okay, what you have to do? You have to take the dot k x3 x1 k x3 x2 k x3 x3 k x3 x4 and multiply by with alpha vectors. This is 4 plus 1 plus 4 plus 1, right? This will become your projection of the third data point on the very first principal component. Okay. Is that part clear? How to do this calculation?
Sir, can you repeat this one again?
So how to find the projection, that part, right? I'm to find the
Yeah, yeah.
projection of the third data point, which is your x3. X3 is your this one, 110, whatever that is. 111, whatever that is, 111, right? I'm to find the projection of this data point on the very first principal component, which is your W1, right? So this is, you have to find alpha 1. So alpha 1, let's say this comes as 4 1 4 1 4 1. Just taking, assuming that this comes as your alpha 1. Okay. It's all,
Yes, sir.
not, it should not be this form, because that is actually unit vector by something. So it is again norm of less than 1. So just assume it's alpha 1. Okay. And then finding projection is just you have to take k x1 x3 plus this alpha 1 the alpha 1 1. This is alpha 1 1, alpha 1 2, alpha 1 3, alpha 1 4. Okay. So 4 plus 4 times this plus 1 times k x2 x3 plus again 4 times k x3 x3 plus 1 time k x3 x4 or x4 x3, whatever. It's symmetric, so it doesn't matter. Okay. So this gives the symmetricity between x1 x3, and this gives the how much importance to give the very first data points, right? So this k function gives the how much these data points similar, and this tells that how much importance to give to second data point. This particular entity gives the how much these data points similar, and this says that how much importance to give that data point. Similarly, this thing. So this gives the projections of the third data point on the very first principal component.
So, sir, basically taking the dot product with the alpha 1 with third column.
Not third column. It's a kernel function value. K x1
Yeah.
x3 x2 x3. It's not the data point.
Actually, sir, this is the third column of the kernel function.
Yeah. That you can call. Yeah.
Third column of the kernel matrix.
Yeah, kernel matrix. Yes.
That is a
Yeah, yeah.
centered KC, right?
It's not KC. We didn't use the centered data point here.
But you said that you have to find this
No, I'm talking about this kernel. He's talking about this kernel functions. Here we didn't center at all. Here we have used only kernel
here we
functions.
didn't, but the process is we have to center it and then find
Then
K, right?
you find alpha K, right? Yeah, that is correct.
Once again, show that KC formula, sir. KC is
KC
equal
formula
to.
is.
So in lecture they have used a different formula. Right?
Yeah, that is wrong.
Yeah,
That is
he
wrong
has
one.
used some theta and all, no?
That is wrong one. You can stick to
That
this
is
one.
wrong. You are saying
That in lectures it is mentioned, whatever Sir has mentioned is not the correct formula. You can stick to this one.
So can you show the formula, sir? Little bit. You can just scroll it up and.
This thing. This is just simple matrix multiplication.
IN
This is matrix
minus KIN. Then
KI.
KIN.
Yeah, this is INK. This is KIN plus INKIN.
Okay.
so. What will be IN
This
here?
is not too
IN is
lengthy for.
IN is the square matrix with all entries as 1 by n.
IN is the matrix of order 4 cross
4 by
4.
4, yeah, the
4 by
square
4.
matrix with all integers 1 by n.
Okay. But is this not a very lengthy process, sir?
Yeah, doing manually these things is very lengthy process. You cannot find eigen, I mean, you cannot solve eigen equations
Yeah,
more than of 3 degree.
correct.
And any kernel function will be more than 6D, sir.
No, a kernel function will not be.
Any kernel function with what?
Now, even if you take a two-dimensional curve, when you project, when you do the transformation, it will be minimum 6 degrees.
Not minimum 6,
You
but
are not
in general it
dealing with
goes
that,
to 6
no?
dimensions. If even with the 2-degree polynomial transformation, it goes to the 6-dimensional space.
But
Yeah.
we don't need to find that phi x, right? We don't
Yeah,
going with
we need not
that.
to find the phi x to find alphas.
But if we are finding the k matrix, then the data set should not be that big. Like we took 4 data points, right? If we take 3 data points, then it is easy, right? Like
Uh,
it should the k will
then
be
you
n
will
equals n,
then you
right?
will get k matrix of 3 by 3.
3 by
Then
3. Then it will be.
then you can do manual calculation. Again, it's a tricky task. It's not easy one.
Yeah, no, but
Yeah, then
we
yeah,
can
eigen
do
decomposition you can do manually by till 3 cross
3.
3.
We did, I think, Math 2 and MLF. So
Yeah, you can find eigenvectors, eigenvalues